Welcome to the fourth video in our series about the C2000 Digital Control Library. In this video we will examine the nonlinear PID controller. As we've seen in previous videos, the DCL contains a wide range of linear controllers and compensators, the structure and tuning of which is well established. Also present in the DCL is a nonlinear PID controller, which can provide superior control performance compared with its linear counterpart. The nonlinear PID, or NLPID for short, shapes the input to each of the three controller parts according to a nonlinear law. The law can be configured in linear mode, so the nonlinear PID can be applied anywhere a linear PID can. Although the NLPID can be used on any C2000 device, the computation of the nonlinear law is typically quite cycle-intensive. The latest F28002X devices incorporate an extension to the TMU to add instructions to accelerate the nonlinear control law. With these in place, the complete NLPID executes in about 117 CPU cycles, compared with 86 cycles for the linear PID, so the overhead is not too much. In this video, we'll take a look at the structure of the NLPID, how to use it, and, importantly, how to go about tuning it. In order to use the nonlinear PID controller, the header file dcl_nlpid.h must be included in the project. Assembly-coded modules, which only run on devices equipped with a Type 1 TMU, such as the F28002X, must be manually added to the project. The file dcl_nlpid_c3.asm is a nonlinear controller, while the file dcl_calcgamma.asm accelerates computation of the linear region gain, something we'll look at shortly. The basic idea behind the NLPID is to shape the input to each of the controller parts according to a nonlinear law. Our nonlinear law is based on a power function, where the exponent is a tunable parameter. To ensure the input-output curve of the shaped law exists in the first and third quadrants, we must preserve the sign of the input, as shown in the red box. The exponent alpha is a tunable parameter, which determines the degree of bending present in the input-output curve. With alpha set to 1, the curve is linear with a gain of 1. Setting alpha to a value different from 1 induces bending, as shown in the family of input-output curves on the right. Here the x-axis is the input and the y-axis the output. The gain through the path is the slope of this curve at each point, so for each value of alpha the gain changes with the input. When alpha is set to a value greater than 1, the gain at the origin becomes 0, implying poor sensitivity there. When alpha is set to a value less than 1, the gain at the origin becomes infinite, which can induce limit cycle oscillation into the loop. Therefore, to ensure good performance, we need to manage the gain around the origin carefully. The NLPID does this by fixing a region symmetrical with the origin and applying a linear gain there. The semi-width of the linear region is denoted by delta, and the linear gain in this region is chosen such that the linear and nonlinear curves intersect when the input equals delta. This ensures we have a smooth, glitch-free transition between linear and nonlinear regions. The linear region gain is named gamma and is computed in the assembly file dcl_calcgamma.asm mentioned earlier. We've seen that the nonlinear law involves computation of the power function, and it is this which dominates the cycle count of the NLPID. There are three ways of computing the power function on C2000. The generic runtime support library has support for the standard POWEF function in C. However, this function is not optimized for cycle count and will take several hundred cycles to execute. This method can be used on any C2000 device. Newer versions of the C2000 FastRTS library include support for the power function. This library computes a reduced precision result in a little over 100 cycles and can be executed on any C2000 device with an FPU32. The most cycle-efficient method is to use the new instructions in the Type 1 TMU, which allow both linear and nonlinear gains to be computed in just 15 cycles. Let's look at this last method in more detail. This slide shows how the nonlinear law is computed using two new instructions on the TMU Type 1. The technique involves computing the power function using a base 2 logarithm followed by a base 2 inverse exponent. Both are multi-cycle instructions, but we can fill the delay slots with other useful operations, such as computation of the linear region gain. Once both results are known, the input is tested to determine which is used. In this way, the complete law for each path reduces to 15 cycles regardless of which region is in use. The code in the lower right is taken from the proportional path of the NLPID_C3 controller. Here we see the structure of the nonlinear PID. The detailed structure in the right half of the diagram is nothing more than a series-form linear PID controller, similar to the PID_C1. The nonlinear blocks on the left are where nonlinear action takes place. The nonlinear law in the proportional and integral paths share some common terms, such as the sign and magnitude of the input, so we compute these first in a preconditioning block to reduce cycles. In the derivative path we operate directly on the feedback, so we must compute the entire nonlinear law in that path. Note that the nonlinear law assumes the input is normalized to plus or minus 1. In this simplified code example, we see the declaration, initialization and use of an NLPID_C3 controller. The code on the left first declares an instance of an NLPID controller, together with its two supporting substructures. The code then initializes its parameters in the shadow parameter set, including the derivative path filter bandwidth. The lines at the bottom compute the linear region gain using the DCL_set NLPID gamma function, and finally the active parameter set is updated. At this point the controller is fully initialized. All that remains is to call the controller function. The code is taken from the NLPID example, which can be found in the examples subdirectory of the DCL. Finally, let's take a quick look at how we might tune the NLPID. In addition to the 3 linear gains, the NLPID contains 2 more parameters in each path, giving a total of 9 tunable parameters. Clearly, the tuning process has the potential to be much more complicated than the linear case. We'll take an approach in which we modify parameters in sequence to improve the transient response. The quality of response can be measured in various ways. We'll use a performance index known as ITAE, for which a function exists in the DCL. The goal is to minimize the ITAE index. We'll start by setting the alpha parameter in all 3 paths to 1 and tuning the controller as if it were a linear PID. The plot on the left shows what we might decide is the best transient response achievable in linear mode. We now introduce nonlinear action into the proportional path by adjusting the alpha_p term to reduce the tuning index. Typically a value will be found which minimizes ITAE, in this case 0.75. Adjustments in either direction will cause ITAE to increase. Next, we try to adjust the linear region semi-width parameter delta_p. In this case, a small increase improved the index slightly. We proceed similarly with the alpha and delta parameters for the integral and derivative paths, finding that we can reduce ITAE from 0.4586 to 0.2262, an impressive doubling of performance through the use of nonlinear action. For more information on tuning, please refer to the Nonlinear PID Tuning Guide, which can be found in the Docs subdirectory of the DCL. This concludes our video on the Nonlinear PID controller. Thanks for watching.